In this video, we'll look at question 5 from the second paper of the 2017 exam. In this question, we are given three statements. The first one is that 10p squared plus 1 and 10p squared minus 1 will be both prime, provided that p itself is an odd prime. Second statement, that every prime greater than 5 is of the form 6n plus 1 for some integer n. And the third statement, that no multiple of 7 greater than 7 is prime. However, the question doesn't ask us to identify the correct statements out of these three, but to say to which of these we could give the counterexample that 91 equals 7 times 13. So let's first go through some definitions. A prime is a number which has exactly two integer divisors. If it only has one divisor, it is the number 1, which is not prime, and if it has more than two divisors, it is a compound number. So it has to have exactly two divisors, 1 and itself. And a counterexample is an instance for which a certain general statement fails. So if I say that all dogs are black, but then someone shows me a white dog, that's a counterexample and my initial statement was not true. And one key thing to realize is that in order for us to be able to find a counterexample to a certain statement, it has to be false. True statements don't allow any counterexamples. And if you read the third statement, you can immediately see that this one is actually true. So assuming they mean integer multiples of 7, so numbers like 14, 21, and 700, well, they are all divisible at least by 1, itself, and 7. So they are definitely not prime. The third statement is always true, and therefore there cannot be any counterexample to it. Again, assuming that they mean integer multiples. So the remaining two statements, they are actually both false, so there could be, technically speaking, a counterexample to them, or there will be a counterexample. But the question is it our counterexample? Is it the one which we were given? But note that the second statement is a statement about primes. So the counterexample would have to go something like, here is a prime, and it cannot be written in this form, like the number 11, for example. But our counterexample is a statement about number 91, which, as they are showing us, is not a prime. And the second statement doesn't concern compound numbers at all. So while it is a false statement, our counterexample is not a good counterexample to it. And how about the first statement? Well, 91 can in fact be written as 10 times 9 plus 1. And 9 is 3 squared, where 3 is an odd prime. And this statement is telling us that provided p is an odd prime, then p squared times 10 plus 1 must be also prime. But our counterexample says, hang on a minute, 91 is 7 times 13. It is not only divisible by 1 and itself, but also by other two numbers. So our statement shows that number 1 is actually wrong, which means that it is a valid, a very good counterexample. And 1 being the only correct answer was in fact option B in the exam.